Okay, let's start. Welcome back to the Edge AI 1 class. Before we start the class, several things I want to mention. First of all, please download the newest version. I added something. I added the Python applications after last lecture, and also I mean, literally just 2 minutes ago, I just realized that I didn't change this, so I changed it to summer 2025. The second thing I want to mention is this one, homework. So I've already uploaded homework one, and the due is next Thursday, I believe. Yeah, the due is next Thursday, 11:59 p.m. MDT is my time zone. In after I finish today's lecture, I mean finish this lecture five, I will spend some time about the homework one. Okay, let's continue our lecture. Before I try, let me still give a very brief review of the linear regression, or I should say LSLR, because this concept is really important. So first of all, those blue points are the training data, and we want to find out a linear function, which is this red line, to minimize the sum of squared error. And mathematically, we can write this form, and by normal equations, we can get the beta solution to LSLR is this one. The details we've already introduced in lecture three. However, this normal equation, this OLS, which is the least square estimator, has an issue that I need to guarantee this x is invertible. In some cases, if it's not invertible, then we'll have problem. Mainly, there are two issues in this traditional LSR. One issue, as we mentioned in the last class, is if n is less than p plus 1, or even n is less than p, then it's guaranteed that this one is non-invertible. Hence, this OLS solution is invalid. Why? Because there does not exist the inverse of this. In practice, it's actually sometimes, if, for example, some biomedical science or those kind of pharmaceutical research, the data collection can be very costly, and hence, you know, maybe the number of observed data points is less than the number of features plus one, and hence this problem will, occur. And we can, of course, use some, tricks to try to avoid this, non-invertible matrix issue. One method is to use the pseudo NP pseudo inverse method. That this is also what scikit-learn package, where scikit-learn linear model linear regression package did in the case. The second issue, or the second shortcoming of the OLS solution, is that some beta elements could have extremely small or large absolute value. I believe I introduced in the very end of the previous lecture. I introduced two cases. Case number one is, I believe, yeah, it's beta 2, beta 0, beta 1, beta 2 is this one. Beta 2 is tiny compared with, all other numbers. So can we drop it? The answer in the traditional LSLR is no, because you have to consider everything. However, in today's lecture, we will introduce two regularization methods, which are called ridge and lasso regression techniques. And you can see, indeed, we can actually doing so by applying some tricks in the optimization model. Similarly, the second case, in the second example, this beta 2, this time is very big, and by comparison, beta 0, beta 1, beta 3 are super small. In other words, this beta 2 coefficient dominates the whole beta vector. Similar things, can we just keep this and remove the other three data? Remove means setting their values to be zero. Again, the answer is both yes and no. No means in traditional LSR, no way you will have to. Yes means, we can use some shrinkage methods to make something, this idea, come true. In general, this sentence is important. I'd better make it in to highlight it in a different color. In general, the more parameter a model has, the more complex it becomes. So whenever possible, we prefer a simpler model with fewer parameters for better interpretability and efficiency. So this is actually the key idea of those kind of shrinkage or those kind of regularization methods. Okay, so here, an idea of improvement is regularization. The benefit of rescaling and the dropping parameters are, if, we can have something rescale, get some rescaling process. This is formally known as shrinkage. If we can have those kind of shrinkage methods, we have some benefits. Uh, the benefits are including but not limited to these four. First is to reduce the risk of overfitting. Overfitting, one thing is from Paul, I believe in the very first page. Yes, this overfitting. This one's ugly because, to be honest, I manually plotted it. That's why it's so ugly. Overfitting again is something that we for example in this data in this example we have 8 data points, and we are using a seventh polynomial to fit it. Seventh polynomial, it has seven coefficients to fit, which are beta 0, beta 1, beta 2 till beta 7. Sorry, it has 8, not 7. It has 8 coefficients. Now think about it. You have 8 data to solve 8 coefficients. So of course you will get an accurate fit. It's just like you have 8 equations to solve 8 variables. In many cases, you get a unique solution. Of course, then it's accurate, but it does not work well. It will not work well for future data. Why? Because it's kind of like overfitting. At a perfectly fit these specific 8 data, but probably not for future predictions. And hence, it's not what we are looking for. You see what I mean? So if now I have lower number of parameters, say here, we have many, say, suppose I have 30 features. But now if I reduce the number of features to be, let's say, 3, then indeed my work will be much easier. Why? Because here we have actually, 7 features. If I reduce it to be, let's say, 2, then it will be better. I can probably avoid the issue of overfitting. Why? Because in this case, I will only have 3 parameters, which are beta 0, beta 1, and beta 2. And we have 8 data points. So, to solve 3 parameters by 8 data points, of course, we will generate some squared error, which is what we are looking for. So this is thing number one that we can avoid, reduce the risk of overfitting. Number two, of course, as we just mentioned, we can reduce the number of features. So people may ask, so what? So what is the point to reduce the number of features? As we mentioned, 2 things. Number one is to simplify the model to drop relatively small coefficients, leads to a more interpretable and manageable model. And number two is to save resources, like those kind of pharmacy, those kind of biomedical things. We may need to add those kind of this kind of chemicals, which are very costly. So if we can reduce the number of parameters, so we can reduce the applications of chemicals, which will save us a lot of money. So these are the main things. Okay, so regularization in detail, what does that mean? So by regularization, we mean to regularize the parameter beta by adding a penalty on a certain norm of beta. So here I introduce something like a norm. I'm not sure whether you probably have learned it in linear algebra, but no worry, we will introduce it. How to compute the norm of a vector. In this lecture, we will discuss 3 kinds of norms: L0 norm, L2 norm, and L1 norm. By Lx norm, what we mean is that we will penalize the beta by applying this X norm from both 0 norm, 2 norm, and 1 norm. Next page, I will introduce how to calculate these norms. And the core idea behind all these regularization techniques is what is to discourage learning an over complex model. This is important, and hence we can reduce the risk of overfitting and get these benefits. Important special case here is the sparse regression. The sparse regression means I want to estimate this beta with a small number of t features, effective parameters or features. So this t must be less than p plus 1. Otherwise, if t is t equals to or is greater than or equal to p plus 1, so what's the point? Because my original data already includes p plus 1 features or p plus 1 parameters. So sparse regression, by the name, it is something that I want to make the beta, the number of effective features, to be smaller from p plus 1 to t. So the remaining p plus 1 minus t parameters will be set to be 0 and hence vanish. That's why we call it sparse. Let me see. Be careful that here, the so-called sparse regression, this term is actually equivalent to drop these p plus 1 minus t parameters. The ideas are similar. However, you cannot you cannot do something as what we mentioned here. Oh, just because this is, let's say this number is small, okay, so I'll make it to be 0. This number is big, so I'll make all others to be 0. No, we need to run a new optimization model. Let's have a look at it. First, we will introduce the L0 regularization. Let me start with introducing the L0 norm. So for any vector A, let's suppose the vector includes p elements, so vector A is in Rp. The L0 norm, the zero norm of vector A is defined in this way, in which this this sigma AI is actually the indicator. Or sometimes it's too complicated to see the math in words, very simple words. It is just to count how many non-zero elements exist in this vector. So for example, suppose A equals to, let me write down here. Suppose A equal to this one. So we simply just need to count how many non-zeros. So this is non-zero, this is non-zero, 3, 4. Be careful, this, even if it's very small, technically it's still non-zero. So we have 4 non-zero elements in this vector A, and hence the zero norm of A equals to 4. That's it. Super simple. Okay, then let's consider the linear regression, the model of linear regression with L0 regularization. So it is in this way. First, the objective function here. Let me make here the objective function here. It is, you can see it is actually nothing but just our linear regression, the LSLR model. However, it does have a constraint, which is here, which is beta zero norm and is less than or equals to k, where this k is a hyperparameter. This k, of course, should be less than p. Otherwise, it's kind of meaningless. Why p, not p plus 1? Because be careful here. We've already, give me 1 second. I think, 1 minute. Wait 1 minute. Let me see here. Yeah, I believe it's just a notation, notation or a definition. Sometimes we can write it just, I just want to make it to be less than p. Sometimes we can make it to be less than or equals to p, which is less than p plus 1. This is really not a big deal because it's just a constant, difference. So this means, okay, now I still want to solve this linear regression problem. However, I do have a constraint that the number of non-zero elements in this beta is less than or equal to k. Again, this k is a given hyperparameter. So our original OLS solution may or may not work for this model. Why? Because we need to count in our OLS the ordinary least square solution, how many non-zeros are included? If the number of non-zeros included in our OLS solution is indeed less than or equal to k, then great. Our OL solution is also the solution of this, linear regression under the L0 regularization. If it's not, say, the total number of the total number of non-zero elements in our OLS solution, which is what I mean is this solution, assuming it exists, okay? It's not the total number of non-zero element is greater than k, then no, we will find another method to solve. If you're interested, this is actually also called least linear regression with best subset selection. Unfortunately, so first of all, this the mathematical model of this problem is actually super easy, direct, and easy. I just want to include at the most k non-zero elements. That's it. I don't want to, let's say, suppose you have p. Let's say p is 100 features. Let's say I only want to ask for a solution which has at most, let's say, 50 non-zero elements instead of 100. However, unfortunately, this problem is NP hard. And even if, for only a moderate sized problem, let's say P is 200, it's not practically solvable, unfortunately, because it is, something involved with mixed integer linear program. It's actually a subject in general, mixed integer MILP. It's not that easy to solve. However, there are some fast heuristical methods to solve. So if you're interested, you can see this. By the way, I want to mention something here in general. As if you go to our course, let's say this is lecture 5. So I've uploaded those kind of extensive reading. They are more actually mathematical, but if you're interested to know the mathematical principles of the techniques we solve, you can read it. As we don't have enough time, I'm not gonna spend the time, introducing this because they're actually pretty mathematical. So this thing about extensive reading. So in general, the problem is NP hard. Again, I'm not sure how many of you are familiar with the term NP hard. NP hard in short means non-deterministic polynomial time hardness. So there are a lot of this is a very famous video, a class I believe by yes by Eric, and he's a very famous a professor in MIT introducing those kind of computing theory, and also, oops, where it is, and also for some description of PMP, MP hardness, you can find here again. Due to a very limited time, I cannot expand it. It can be multiple hours. That video is actually very, very good if you're interested. It includes most things for a basic understanding of P, MP, and MP hard or MP completeness, the classifications of those classes. And the one interesting thing I want to mention is that the famous problem P equals to NP till now it's unsolved. If you can solve it, you will get 1 million from CIMS. So this is the thing. But in short, you just need to know that this model is beautiful. Unfortunately, it's not practical. We cannot easily solve it, even give a super small sample like P only equals to 200. Okay, then how to improve it? You cannot say it's not solvable, so we completely, give up this regularization idea, right? No worry. We will move to L2 norm, and in the extensive reading, you're gonna see that if the columns are orthogonal, then actually we can get an analytical solution, which is super, super powerful. Okay, so we will start with the idea. Clearly, the computational trouble of LRBSS comes from the L0 regularization because you need to count, hey, how many zeros? No, sorry, how many non-zeros? This is actually very difficult. However, if we can apply another norm, the issue can be easily solved. For example, here we use 2 norm. The L2 norm. The L2 norm is actually the Euclidean norm, which is nothing but the square of every element of a vector, then make a square root of this. So for example here, let me just, for example, suppose my a equals to, my a equal to this 0, 3, 0, -4, right? What you need to do is just make the 0 square plus 3 square plus 0 square plus -4 square, and you can get the total answer is 3 square plus 4 square as what is 25, right? And then make a square root of 25, which is 5. And hence, it's the true norm of this a is 5. It's just super simple. This is actually the distance, the Euclidean norm, the distance in our real world. And okay, so similar things, we're gonna, the linear regression with this L2 regularization is to solve this problem. And again, you can see here, the objective function is again the same thing with our, traditional LSLR, but we have a constraint again, which is here. And compared to the previous zero norm, sorry, it's still here. Compared to this, the only difference that here we change the norm to be 2 instead of 0. Of course, we change the right hand, the name of the right hand side hyperparameter from k to t. So I mean the name is not a big deal, but the big deal is here. The norm is 2L2 norm instead of L0 norm. This problem is actually very simple to be solved. Why? Because this problem is a convex programming problem, and it's easy to show that the Lagrange form of this problem, which is nothing but just to add, this objective function, move it up to this. And then I add a lambda parameter. This lambda is related with this t. And I believe, I showed an example, a calculation of in the extensive reading how to convert this lambda from t. But just to let you know, this one is associated to this t. And then this problem becomes what? Let me just add a box here. This problem becomes an unconstrained optimization problem. You can see this one is constrained. I need to satisfy the L2 norm of beta is less than or equal to t. But this one, no, I don't have these constraints anymore. And since, this is a convex program, a quadratic problem, which is a convex problem, it's very easy to show you that the solution of these two problems are the same. And hence, I just need to solve this one. Why this one's preferred? Simply because there's no constraint, makes solving it much easier. If you're familiar with those convex programming, this one just makes the derivative. You can directly get the solution, which is super simple. Again, here, this lambda is a non-negative hyperparameter, which is, you can consider it as given because t is given, so, this lambda is given, non-negative, okay? So this is the idea. Okay, so let me see here. Oops, sorry. This is actually an in the illustration graph of the ridge regression. By the way, this is called a ridge regression, this model. First of all, it is a parameter shrinkage model. So why do we say it's a parameter shrinkage model? Okay, consider this. So suppose this point is the beta OLS, which is the solution of our LSLR, the traditional one, which is given by what? Given by this beta. This is OLS solution, okay? And of course, here we suppose this solution exists. Otherwise, it's difficult for us to show this illustration figure. So suppose this one is OLS, and we can actually plot the contour of the RSS here. Recall that we are to minimize the RSS, right? So I claim that this one is the solution to my ridge regression, which is nothing but the tangent of the first RSS with this region. So this is our, we're talking about the original model. This is our domain of the ridge regression, which is, so for convenience here, I assume beta has only 2 dimensions, which is beta 1 and beta 2. So by the Euclidean norm or L2 norm, we have beta 1 square plus beta 2 square as less than or equal to t. Here I put a square just so that I don't need to have the square root, make my life easier. by this kind of like high school knowledge, you know that it must be a circle, and less than or equal to t means the radius of this circle is t. So let me see, how can I plot? Give me 1 second. Let me just plot the clips. I hope it's not too ugly. So you can see, no, never mind. Let me plot by directly by my mouse. Please excuse me. It's not going to be very beautiful. So, if we increase the RSS, for example, for example, this radicate may be RSS, let's say, equal to 120, the contour. And then you can see that because we try to minimize the RSS, and hence clearly this tangent is the best solution. You see what I mean? Why? Because if otherwise, if I don't take this tangent, first I cannot make it smaller. Say for example, for example here, for example here it doesn't work. Why it doesn't work? Because it's out of your domain. And also, let's say here it is a feasible solution, but it's also not the ridge beta. Why? Because this RSS is too small, too big. This one is the smallest I can find. Okay, so now let me remove it. So now let's see why it's called a parameter shrinkage. Indeed, you can compare my R beta ridge versus my beta OLS. You see the point? No matter in the direction of beta 1, which is here, so this is beta 1. See it? You can see indeed the I don't know why Zoom is so big. This one looks like I cannot make it smaller. But so this is the beta 1 or in the OLS. By comparison, this length is the beta 1 of my beta ridge. Did you see it's a shrinkage in the direction of beta 1? It's smaller. Okay, similar things. If we have a look at beta 2, so from here to here, this is a beta 2 of my beta OLS, and this is my anyway. Let me directly plot a line. Okay, so this is my beta 2 in my beta OLS versus this is my beta 2 in my beta ridge. It's also shrinkage. You can see no matter from which direction, my beta ridge, the corresponding parameter, is a shrinkage compared with beta OLS. And hence we say that ridge regression can, produce can perform a function which is parameter shrinkage. So that is the reason. And actually, I believe in my extensive reading, I provide a formal algebraic proof, which is if x columns are orthonormal, then we can get the exact shrinkage factor, which is 1 over 1 plus lambda, section 0.2. It's actually, let me just directly open it here. Which is here. But again, I mean, this is absolutely not required in this course. Just in case, if you're interested, then you can calculate. You can see and calculate the exact parameter shrinkage level. We can see that a beta ridge equal to beta OLS divided by 1 plus lambda. So that's the thing. Okay, let me see where it is. And also, it can somehow solve the issue of this one, of the non-invertible of XTX. Why? Because I just closed it, sorry. Why? Because we have, let me see, it's also 1.2, I remember. It's right here. By adding this one, I will no longer need to strictly calculate this one because it will be involved with a lambda. You see what I mean? And hence, I just need to solve this. So why? It's possible that, for example, if the XTX is not invertible, but add this one becomes invertible, because it's corresponding to add a lambda parameter in the diagonal elements. Remember what is I? I is the what the let me write something here. So I can have, oops, sorry, here. I can add a lambda, lambda in the diagonal of my identity. I is my identity matrix. So by adding this, I will strengthen this lambda is non-negative, okay? I will strengthen our diagonal elements, and this can effectively eliminate the issue that XTX is not invertible. So that's the second good thing. And and the third thing I want to mention is that some readers may ask, so why do you claim that the RSS contour, equivalent contour is ellipse? Why isn't it, for example, like a circle or square or something? That is because, my RSS is defined in this way. So you can actually, expand it to be this. Be careful here, beta is my parameter, okay? So the quadratic coefficient the coefficient of the quadratic form of beta is xtx, and this is for the coefficient of beta itself, and this is the constant. You can ignore the constant. Here, we can claim that determinant of xtx, this one, is greater than zero. Why? Because we assume the beta OLS exists, and hence it's invertible, and hence the determinant must be strictly greater than zero. And then if this coefficient is strictly greater than zero, then if you see here, it's a conic sections, the Wikipedia, and then this will tell you that it will be, I think here we go, Q is ellipse if this one determinant is greater than zero. And I know this is only for two dimensions. Actually, for a hard dimension, let me see here where it is. Up let me see. I believe. Here we go. Let me see. Degenerate. No, here. It's ellipse. It's. Let me see. I remember before they have a very common conclusion instead of only 2D, because this is more like 2D. No. It's the same. It's the same because A33 is defined in this way, which is here. And by reading this, you can see that indeed, because this determinant is strictly greater than zero, and hence it must be an ellipse. It's not like I just accidentally plotted. It can be proved that the contour RSS contour must be an ellipse. So that's the thing. Okay, so after seeing this R2 regularization, we are gonna check another technique, which is R1 regularization. Again, first of all, let me introduce what is the L1 norm. L1 norm, we call it like a taxi cab norm. Why? Because it measures distance like a taxi driver through city blocks. So it just counts. I should say it just adds the absolute value of each element. That's it. So again, for example, if my A vector is in this way, so I just make it a zero absolute value plus a three absolute value plus zero absolute value plus -4 absolute value at equal to 7. And hence the L1 norm of A is 7. Okay, so let's have a look at the model. Similar things here. Our objective function is the traditional least square linear regression model, but here I do have a constraint, which is the L1 norm of this beta must be less than or equals to t. And similar things, we can use the Lagrange form, move this to my objective function. And hence my new model, which is equivalent, becomes this model. And we can see this model is an unconstrained model, unconstrained optimization problem. And to solve this one, in general, is easier to solve this one. So we call this one as Lasso regression. Similar things, this lambda is a regularization hyperparameter. You can just consider it as a given parameter. Later, we will introduce a technique called cross-validation methods to figure out what value lambda should be. But here you can just consider it as a given hyperparameter. This one again is non-zero, so as non-negative. Okay. So let's have similar to the ridge regression, let's have a geometric interpretation of the ridge regression. First of all, we need to pay attention to the feasible region of the ridge regression. It becomes a diamond. So why the ridge regression is a circle, but in my lasso regression, it's a diamond? Because we need to have a look at the constraint. So in my ridge regression, my constraint is in this way. And hence, if beta is 2D, we can see it is equivalent to beta 1 square plus beta 2 square is less than or equal to t. This is, I believe, just use high school knowledge, you're going to know, of course, this is a circle. However, here, my equation becomes one norm, L1 norm of beta is less than or equals to t. And again, if it's 2D, so we have beta 1 absolute value plus beta 2 absolute value is less than or equal to t. Again, this t is given. And you can see it's indeed, a diamond. If you don't believe, very simple thing, let's assume beta 1 and beta 2 are both greater than or equal to 0, and hence it becomes beta 1 plus beta 2 is less than or equal to t. You see what I mean? Or you can say x plus y is less than or equal to t. Then the line what will be this line. You see it? And the corresponding region gonna be this small region. And similar things you can discuss 4 different cases, which is beta 1, beta 2 both greater than or equal to 0, beta 1, beta 2 both less than or equal to 0, and the third case is beta 1 is less than 0, but beta 2 is greater than or equal to 0. And the fourth case is this, which is beta 1 is greater than or equal to 0, and beta 2 is less than or equal to 0. And by combining these 4 cases, you will get this diamond feasible region. Okay, now similarly, let's plot the RSS contours. And suppose this point is the beta OLS solution. Again, to make my life easier, I assume this one exists, Okay, so I have those contours. Similar reason, it must be ellipse. Okay, then you see the point here. My solution gonna hit this point. Why? Because this is the first, with the increase of my RSS contour, this is the first point that hit my feasible region. So it's gonna be here. Then people may ask, so okay, looks great. So what is the point? The point, this is a very, very important point, is that here it occurs at a corner of the feasible region. Corner means, for example, here it means this beta lasso only has beta 1. It does not have beta 2 anymore. You see the point? This means I have successfully reduced the number of parameters from 2D to 1D. Why? Because here there's no beta 2 anymore. I can just ignore beta 2. I can just make it to be beta 1. That's the thing. And later you will see examples, something that we can significantly reduce the number of variables, for example, from 1,000 features, reduce it down to only 30 features. This is gonna significantly simplify your model and save your budget in your future observations or in your future tests. And the similar things here, should I have one here? Oh, look, I didn't. It's let me see where it is. 2.2. I showed a formal proof why it has both variable selection and a shrinkage. Oh, by the way, I forgot to mention, sorry. I forgot to mention that first of all, it's a variable selection, which is here I've reduced my beta from 2D, which is beta 1, beta 2, to 1D, in which in this beta lasso, you only need to consider beta 1. You can ignore beta 2 as it vanishes to 0. The second thing is it's also a shrinkage. Why? Because even in terms, oh, sorry, let me plot it this way. Even in terms of beta 1, you can see this is the length of beta 1, right? The coordinate of beta 1 in my beta OLS. And this is my beta 1 in my beta lasso. You see what? Clearly, this in beta lasso, the beta 1 is smaller than the beta 1. Smaller means the absolute value, okay? Absolute value is smaller than the beta 1 in beta OLS. And hence, what? It has a shrinkage. And in section 2.2 of this extensive reading, which I used to teach in NDSU several years ago, it can show you a proof that it does have a shrinkage and also variable selection of both. The main part is here if you're interested. But in terms of this super small short course, no, it's not required. So this can show you the power of lasso. It has both shrinkage and a variable selection. Then people may ask, so As Lasso is so good, so why do we even need to introduce the ridge, right? We just use Lasso, done. There's an issue here that ridge regression does have an analytical solution, which is perfect. And it can address the issue if XTX is not invertible by choosing an appropriate lambda. However, in Lasso, you do not have an analytical solution. You do not have a closed form at all. Sometimes to solve a Lasso solution, it could be pretty time consuming. Although we sometimes, we can have those kind of iterative algorithms from Lars. It's one of the gradient method and also least angle regression, which is Lars. But these are all heuristic. It do not guarantee in any cases for a closed form. I mean, it doesn't even exist. Not to guarantee, it doesn't exist. And for these two, it could be pretty time consuming if you have a large number of features. And also it cannot avoid or address this issue. And hence, I would say, well, if your data size, the size of your data, I mean, the number of features, and the number of observed data points is not that big, absolutely, you should try Lasso. However, in some cases, if Lasso the result, it takes a long time to solve, or even let's say you cannot solve it, then you can, get a ridge. Although ridge regression in general does not provide you parameter selection, at least it will give you parameter shrinkage. It will make it, your solution to be more standardized instead of something like that, which is what I'm talking about, this extreme case, which is, oh, this one is huge and all other things are relatively small. No, ridge regression can greatly address this issue, actually. Okay, so in the previous, introductions of both ridge and the Lasso regression, we mentioned that, hey, we have a hyperparameter lambda, which is non-negative, and I said you can consider that it's given. But in the practical issue, oops, sorry, in the practical issue, how can we choose this hyperparameter, that lambda? This is gonna be, a practical issue. So we actually have many methods to choose those kind of hyperparameters. Remember, before when we mentioned the data splitting, I said that there are three sets. Set number one is a training data set. Number two is a validation data set to handle those kind of things. And number three is the test set, which is to give you a final view of the model that you have trained. So here we're going to talk about the validation data set. And among many methods, here we will introduce one of the most famous methods, which is called a cross validation. So cross validation is to tune this hyperparameter based on a metric. So we from for example, before we always mention RSS, but typically in cross validation we use MSE, mean square error, and here's the formula. I mean mathematical formula of MSE. It's actually equivalent to RSS. Why? Because the difference is just a constant. Because once your training data set is given, this n is a fixed number. It's no longer, it's a constant. And hence, n 1 over n is a constant. In other words, we can see that the mean square error versus the RSS, the only difference is just a constant before it. Hence, we can say comparing MSE is equivalent to comparing RSS. Okay, so now let's see how can we make it. In this class, we will focus on the k-fold cross validation, which is one of the most widely used techniques in cross validation or in the whole, those kind of hyperparameter selection. So this is actually the pseudo algorithm of the k-fold cross validation. Let's first have a quick look at it, and then don't worry, I will give you detailed examples to get it. So first of all, we randomly partition the entire observed data set, including both training and the validation data, into k equal sized groups. these groups are called sample groups. And you can see k equal size groups, and hence the name k-fold cross-validation. Okay, now we will retain one group, let's say group I. Initially, we will choose I equals to k, and later you will see we'll set I equals to I minus 1. It will make it down. Choose group I as the validation data set, and the other k minus 1 groups as training data set to train the models. Okay, now we'll just train the models. Remember model.fit. And then after the training, evaluate the performance metric of the model. So here we're going to use MSE based on the validation data set. So the training data set is for training. So after training, I will choose the betas, right? And now I will calculate the MSE, the performance metric based on the validation data set. Then I will set I equal to I minus 1 and go to step number 2. So in the beginning, group K, the last group will be the validation data set, and the first K minus 1 groups will be the training data set. Now I'm going to choose the second, the K minus 1 group to be the validation data set, and then the other K minus 1 group to be the training data set, and just make a for loop or make a loop of this until I've finished, which is I've repeat until every group has served once as a validation data set. Then I'm going to compute the average of this K MSE. So here it's going to be MSE K, MSE K minus 1 until MSE 1. Then I compute the average of this K performance matrix. And this average value represents the metric for this given parameter lambda. Okay, so now I can have a candidate set of lambda, which is lambda 1 till lambda t. So recall that here for each lambda, I can have the average value of this lambda, and then I'm gonna compare these t average MSEs, and I will finalize or I will select the lambda equal to lambda j star, which this j star has the smallest corresponding average MSE. So that is how we do it. Again, don't worry, we'll see an example here. And the one thing I do want to mention, which is important, that the same partitioning is used across all candidate lambda j values. You don't have to, let's say, for each different lambda, have a different partition. No, we do want to have the same partitions. Why? Because we want a comparison to be fair. In addition, other than the k-fold cross-validation, we have some other methods. Two other well-known methods are the AIC and the BIC. For sake of the time, I'm not gonna mention it here, but if you're interested, you can just click these two links. They have the Wikipedia links, and also Scikit-learn library has the corresponding methods. You don't have to write IRC, BIC by yourself. Okay, so let's have an example to explain this k-fold cross-validation method. Okay, so first of all, First of all, consider the candidate lambdas are 1, 1.5, and 3. Sorry, and 2. These are 3 lambdas. Excuse me, let me drink some water. Okay. These are 3 candidates. Okay, suppose we have 8 observed data points, which are D1, D2 till D8. And by the way, here observed data points, what I mean is the test and the validation data set. It does not include the, here, what I mean, 8 observed data points are the training and the validation data set. It does not include the test data set. Suppose my K equals to 2. Okay, that means in each fold, 4 data points, 2 big, because 8 divided by 2 equals to 4. And hence 4 data sets are used for validation and the 4 are used for training. Okay, so now first of all, I randomly partition the data. Let's say suppose the partition this way is 4, 3, 8, 1 as the first fold, and the second fold is going to be D7, D6, D2, D5. Okay, now first of all, recall that we will start, sorry, here, where it is. We will start with I equal to k, meaning that I will start by choosing the last fold data to be my validation data and all other data points being the training data. And hence, this is the last group or the last fold. This is the validation data and all other. Since here we only have k equal to 2, so only two groups. So this one gonna be the training data. This one gonna be the validation data. I should say data set. Okay, now I'm gonna do what? I'm gonna train the model based on the training data points. In other words, I'm gonna train the model based on data 3, data 4, data 3, data 8, and data 1. And then I'm gonna calculate the MSE using the beta trained here. So I'm gonna calculate the MSE11 based on D7, D6, D2, and D5. Okay, now I get MSE11. Then the name cross validation, meaning that, okay, this time I will move this one across the training and the validation data sets. Did you see it? So this time I will use this data group, this fold of the data points to be my validation data, and this data points, this fold to be my training data. And hence, I'm going to train the model based on D7, D6, D2, and D5. And then I have the parameters betas, and then use this to compute the MSE based on the validation data, which is D4, D3, D8, and D1. And hence, I will get MSE 1, 2. Now, I will determine MSE1. What is MSE1? Which is the mean or the average of MSE11 and MSE12, which is 1 over k of this. Here, of course, my k is 2. I have only two subgroups, or I have only two folds. So here it's going to be half of MSE11 plus MSE12 here. So now I get the MSE1, which is corresponding to my lambda 1 equals to 1.0. Do the similar things, I can calculate the MSE2 for lambda 2 equals to 1.15, and the MSE3 for lambda 3 equals to 2. I will repeat the same thing, but be careful here. Do not repartition the data. In other words, even if I'm computing, the MSE2 for lambda 2 and the MSE3 for lambda 3, I will still use this compartition, which is the first subgroup of the first fold of data going to be D4, D3, D8, D1, and the second group going to be D7, D6, D2, and D5. And then now you have MSE1, MSE2, MSE3 corresponding to the three lambdas, right? Then you can see, okay, which MSE is the smallest. Then you will choose the lambda with the smallest corresponding MSE. That's how we do it. Several things. Everybody gets the point. So suppose my MSE1 is 100, MSE2 is 200, MSE3 is 300. So of course, MSE1 is the smallest, and hence I will choose lambda 1 as my hyperparameter. So that's the thing. Second example, similar, but this time we have three groups, k equal to 3. So suppose I have 12 data points, observe the data points. Again, here, observe the data points, what I mean was for training data and the validation data. It does not include the test data set. Okay, now, totally 12 data points, k equal to 3. 12 divided by 3 is 4. And hence, I will choose every 4 data will be one fold or one sample group. So suppose I randomly, partition it. Suppose the partition is this: D10, D5, D1, and D2 to be the first group, D12, D9, D11, D7 be the second group, and the D6, D4, D3, D8 to be the third group. Again, we'll start by choosing the last the last group to be the validation data. In other words, I will train the model based on the first, 8 data. So I have the betas, and then I use these betas to calculate the MSE11 based on the validation data, which is based on D6, D4, D3, D8. Then cross validation, which is in the second iteration, I will move, I will choose, remember, I equals to I minus 1. And hence, I will choose currently I equals to 3. So 3 minus 1 is 2. So I will choose the second subgroup to be the validation data. And the other, these 8, these eight data to be the training data. Again, I can get the corresponding betas, and then I will use these to calculate the MSE12 based on my validation data. So I will get what? I will get MSE12. Again, cross-validation. This time I will choose the first group, subgroup to be my validation data, and the others to be my training data. And again, I get a betas, and then I can compute the MSE13 based on my validation data. So I have MSE13. Then, because of k equals to 3, I can calculate the MSE1, which is corresponding to my lambda 1 equals to 1.0. This one equal to 1/3 of MSE11, MSE12, MSE13. So, which is the average. And then, this MSE1 is corresponding to my lambda 1. Similar things. I can calculate MSE2 for lambda 2, MSE3 for lambda 3. And then I will just compare these three MSEs. So which one is the smallest? Then the corresponding lambda will be selected. That's the thing. Good thing is in Python, in scikit-learn package, you do not have to write everything by yourself. I mean, it's already included, but I think you'd better know what is cross validation because it's just too common. You don't have to really code it by yourself. I mean, if you would prefer, which is great, but you don't have to. At least you can know what does it look like, what is it for? Because later, I mean, you will see too many hyperparameter tuning or selections are by cross validation method. Okay, so now let's code it. I will show the lit coding, but before it, I do want to mention one super important thing, which is here. So remember, before what we did is we first got those kind of x and y's, and then we use self.xtrain self dot x test y train one test equal to the what linear model dot model selection dot split. Remember this one? Let me show you what I'm talking about. Let's say suppose I go to lecture 3. So what I mean is this. Where it is? Here we go. So here we do have, model selection dot task train task split here. Why? Because we want to randomly split to be the train the test data, the training data and test data, right? By the way, validation data itself is included in the training data. Okay, but here in this very where it is. Okay, here in this very specific example, I fix the training data to be the first totally there are 100 data. 1 minute, sorry. I'd better let you have a look at the data point first. So I believe, wait a minute, where's my path? Give me 1 second. I just want to make sure. Where's my main function here? The path. Yes. This is yeah, you can see the name example 3D. So I do have 100 data points and it has 6 features. The one we used before. Okay, so now here, I do want to fix the first 70 data to be my training data and the last 30 data to be my 60 data, to be my test data. Uh, be careful. The purpose of this is just to fix the output. You see what I mean? Because in this case, I can tell you, okay, the output will be fixed to be this way because it's always, otherwise, if we don't do this, then if we still use, the training test split as what we did in lecture 3, then every time the output will be different. So it will be very difficult for us to compare, because here I'm going to compare the L's, LR, compare the ridge, compare the lasso. It will be very difficult for me to compare it. The only reason I set up here is just for this specific example. I want to make it clear, okay? In a practical problem, you are not, okay, again, I want to make it clear, you are not supposed to do it this way. You should do what we did in lecture 3, which is to use the train task split to get a random split of the test and the training data. But here, I fixed it just to fix the final output and to compare. That's the reason I do it here. At this point, I'd better explain it carefully because otherwise I just worry like in the practical problem or project, you still do like this way, then clearly it's wrong. You're not supposed to do so. Okay, so now let's go to the anaconda. I should be able to finish this lecture pretty fast because I do want to mention something about the homework 1. Okay, so let's wait a little bit. Okay, here we go. So I in class, I believe this is lecture 5. oops, lecture 5, linear regression 2. Okay, now let me open a notebook. Let me rename it to be rename in class lecture 5. Okay, so first of all, I need to upload the data here. Super simple. You just need to you you just need to open the wait a minute. Why there? You just need to drag, choose these two, drag here. The second data that I'm going to run is a bit big. It's a 55 ASCII. Do you still want to upload it? Yes, I still want to upload it. Whilst uploading, we can just save our time to just, let me see, increase it a little bit. Okay, and then again. Okay, so I added the column number, the row numbers here. It's exercise 5.3. Okay, let me make something exercise 5.3. Oh, sorry, markdown. Okay. So now let's see how can we make it. So what we need to do is we first need to remember what we did is we make it to be a class um, of the linear regression, and after it, I will write functions to compare as LSLR, ridge regression, and also lasso regression. Okay, let's see. First of all, we need to import numpy as MP, import pen does pd import sklearn, and do I need to import a matplotlib? Oh no, because here I'm not gonna plot anything, so I don't need a matplotlib. So I'm gonna from sklearn I need to import a linear linear model. It doesn't come. Okay, okay, here we go. It's a bit slow. I'm just pressing the table to make it easier for me in case of misspelling. From sklearn dot matrix import mean squared. It doesn't show, but it's mean. Okay, here we go. Mean squared error. Okay, so now I will create a class as what we did before. Linear regression compare. Let's say compare. Okay, so now first define initialization things again self, and then here we have a path to import. Put a path there. Self data equals to pd dot read csv path. Okay, and the second is that the x self x equals to self dot data dot job. We're gonna job. It's called y. The head is called y. Be careful. This y, for example, if it's a y-axis, then you're gonna make it a y-axis. You see what I mean? If the name is too long and you're tired to copy and paste here, what you can do instead of directly put a name, you can just say self dot data dot columns, and then you can say which are columns, 0. Remember we mentioned this before. But here, since it's relatively easy, so I'm gonna save some time. I'm gonna simply get a y, and then don't forget the axis equal to 1, meaning that you're gonna drop a column, and then self dot y equals to self dot data, and then here's easier, just y. Okay, so now after this, we'll do what? We will get the data for X train and Y train, X test, Y test, right? Before we use a split, but here again we will make X train equal to self dot X 70, meaning that the first 70 data gonna be my training data. Again, the reason for the reason you can just read here. Okay, to save time in the class, I'm not gonna mention it. And then self dot y train equal to similar thing, self dot y 70. And then I'm gonna make self dot x test equal to self dot x negative 30. Oops. And then self dot y test equal to self dot y negative 30. Okay. So now this is, for the initialization of any regressions. And now I can have defined else LR self to LR equals to a linear model regression. That's here. And then similar things. Here, again, you can definitely make it to be self.lr, but here to make my life easier because I know I will not cite it again. Hence, I did I didn't make it as an attribute. I just make LR to be a transient variable, or I should say transient object. LR dot fit self dot x train and then self dot y train. Okay, so now I'm gonna have R2 to calculate the R2 coefficient equal to LR dot 4, and then similar thing, self dot com dot train x train. And now I can get the y predict equal to LR dot predict. And then print. I'd better say else LR as R2 dot 3F. And now I can print the coefficient theta 1 dot 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 theta, let's say self dot x dot shape 1 R COEF. Oh, I'd better set up the precision, otherwise it will be very, very long. And hence I fix it the precision to be 3. And then I'm gonna after this, let me have a look. I forgot. I guess MSE. Yes. I'm gonna print the MSE and then let me see and predict. Okay. So now I'm gonna print the MSE on the training. Square error. Okay, so first of all, have a look at the what formula of MSE. For MSE, you see, you need to compare the true Y versus the estimated Y, and this estimated Y is trained by your training data, and hence here I will have two things here. Oh no, it doesn't show the help. So here, in MSE, the function it will ask you, hey, which two will you compare? So what I want to say is self.y train, which is a trained Y, versus this trained Y. What I mean is the real Y, okay, the true value versus self.y per. Wait a minute, wait a minute. I need to. No, I've already have the predict. Y predict, and then I can just have well. Let me have a blank line here. So this is what we did for the what? For the Lasso regret. Sorry, this is what we did for the LSLR. And we can, wait a minute, I have one more thing here. Wait a minute. We also computed for training data for, okay. Okay. What I did here in the code is that wait a minute. Here wait a minute. I'm wrong here. Give me 1 second. Here the test there. Sorry. I should make it this way. Give me 1 second. I should make it first of all. Let me just copy and paste here. I should make it for both test data and the training data. And here I'm gonna have self.y test. So I want to see the MSE of the test result. And then here is the Y PRED. The Y PRED is what is this one, the test data. So sorry, here as well. And then I want to do it for my training data as well. And hence I will have a water predict training, excuse me, equal to LR dot predict and then x self dot x train, self dot x train. And okay, so now in that case, I can make mean square of this one, x train versus the y predict x train. But y predict train, which is here. So this is to compute the MSE in the test data, and this is to compute the MSE for the training data. I believe I did this is because in the output, you will see the comparison for the three techniques, which are LR, ridge regression, and also lasso regression. Okay, so this is the what? Let me just run it just in case. Everything in case of any issues. Main function, and then I will need to have the path. So the path equal to, I will just copy and paste, rename, copy, and then paste, and then paste. Okay, so now I'm gonna say LR6 equal to linear regression should be a class. Hey, give me. Okay, linear regression compare. This is a class and a path. And now I can say LR6 dot LSLR, which is, yeah, here. I just want to make sure everything's correct because I will copy and paste. Okay, great. So here's wrong name. Oh, wait. Wrong sparrow, compare. Let me see. Okay, here we go. There are 22 print options printed wrong again. Why predict is wrong? Why parity is right here? Why says there's no self.y predict? Well, one minute. I know why. Because let me see. Did I use it? No, no, no. So if that case, I don't have to make it a self.y predict. I can make it just directly y predict because I don't have to make y train the similar things. So I don't need these two. So I make these variables to be transient variables so that I don't need to save them anymore. Okay, great. So this is the result of my LCLR. Okay, so now I will code similarly for, let me say this is, and this will be for ridge. And I can simply just comment and paste. Let me see. I use ridge R or I use ridge. Let me see. I use ridge R. Okay, so I'm gonna I use the ridge things and then ridge version one here. So I can just copy and paste everything from ridge here. So LR to the ridge R, and then R1 LR here, ridge R, and then here, ridge R. Oh, the coefficients of ridge regression is R2. Wait one minute, R2 is here, and then I should have one ridge out of double R. And then let me see here, coefficients of this is ridge R. Dot coefficient and MSE here, self. This is still the same. One predictor is updated here, and then here's the rich R, and here, just make this one here. Okay, here we go. So now let me just run it as well. RR6 dot ridge. Okay, great. I believe I added something extra. Give me a second. I forgot. The test data here, ridge here. Okay, I need to print the select lambda by cross validation here. So it is, dot alpha here. It's, let me just add it here. In the region, I will add one more thing. I will print the lambda via cross validation is selected to be. Come on, it doesn't come. Okay. And then we'll process alpha. How come? It must have. If you, okay, that's why. Sorry, here's wrong. I cannot use LSR regression anymore. I should use ridge CV should be uh model. Come on, it doesn't come. Okay, ridge R. What ridge R? Ridge C. Why it doesn't come with ridge CV? It should be ridge CV. Give me one second. Let me see. Yes, it is a rich CV. Why doesn't show me anything here? Give me 1 second. I just want to make sure my what is correct. My 0.71, 1.79 here. Let me see where is 1.79 here. Uh, where's my beta zero? Interesting. Looks like I didn't. I forgot to print the beta zero. Sorry. The R square here. I need to print the beta zero. Okay, so things here. Okay, here we go. So let me see whether the conclusions are same. Otherwise, something's wrong. Okay, good thing. It is the same. So here we go. Yes, because before I forgot to update the model, the classifiers, the regression methods. So, and similar things, I can just simply copy and paste for Lasso. Okay, so replace this by Lasso. I need to change this one as well. I will have 1 minute, something's wrong, 1 minute, 1 minute. Because here I consider the alpha, I need to have a alpha list, or I can call it a lambda list. So this alpha, this alpha is something, remember here we mentioned a list of your lambda. Unfortunately, in scikit-learn package, it's called alpha. It's not called lambda, but the same thing here. So, oh, sorry, the same thing here. And then we can make kind of like a lambda list to record this alpha. So here, what I'm gonna have in my main function is I will create a lambda list. Lambda list equals to, let me see, what did I use in my slide? Equals to 1, 3, 5, 10, 20. Okay, 1, 3, 5, 10, 20. 1, 3, 5, 10, 20. So that I can put, add this lambda list as an input here. So that I'm gonna say, give me 1 second, give me 1 second here. I need to add something which is lambda alphas. Here it's a keyword, and you can see alphas is here. So if you don't write anything by default, the alpha is going to be set to be this way by the scikit-learn, building cross validation. However, if I don't want it, I can just equal to a lambda list. That's it. So if I don't write alpha to by default, use these alphas. If I write, let's say alphas equal to lambda list, then I will use my, designed alphas. Okay, so now similar things. Let me see what here, Ridge and also here, and a lambda list. So here, it's not going to be a Ridge CV, it will be a Lasso CV. .com. I guess large Lasso is so CV. Yes, here I go. So that alpha is equal to a lambda list. Okay, so now I'm gonna replace Lasso R, Ridge R with Lasso R. Here, y predict is also here. Coefficient on Lasso regression is this one, and interpret this one as Lasso R. Precision coefficient here also Lasso R. And then mean square around y test, this is correct, and then this is going to be Lasso R as well. And then train square here, and then also in the Lasso R is here. Okay, here we go. So now our here we go. Okay, wait, which part is wrong? Lambda list one. What? Why the output is two? Oh, here. It's not LSR. It's I just ran the ridge LR6 dot lasso uh down list. Okay, here we go. So as we can see, this is the R square of what? The R square of LSR, and this is R square of ridge regression, and this is uh, the what? The lasso regression. In general, of course, the LSR should have the best result. Why? Because LSR is something like I don't give you any limitation. You directly tell me the true minimum RSS. While Ridge and the Lasso, they do have a constraint, which is the L1 norm or L2 norm of beta should be less or equal to something. So that's the thing. And indeed, here you can see that we have what? Let me just underline it, makes it more clear. So so this is my LSLR, this is my Ridge, and this is my Lasso, right? First of all, you can compare. Do you see the corresponding, in general, it is like a shrinkage. I know this one may be not that big. These two are small, but look at here. You're here. The absolute value, there's a shrinkage. See it? This one is a bit more. It could be those kind of, because I make it to be like a 3.3 digits. It could be, but in general, it should be a shrinkage compared with LSR. And here is Lasso. And Lasso, you can see it's not only the shrinkage, but also, for example, have a look at this. This is beta 1, 2, 3. The beta 3 is directly 0. This means what? This means in my future examples or in my future like data observation, I can just eliminate this feature number 3. I can only use features 1, 2, 4, 5, 6. So this is actually an elimination. Get clear? So this shows you actually a pretty good, sorry. This actually shows a pretty good first example of the three linear regression techniques. They're good and bad points here. So here I'll mention something, in general, it is that the thing. And yeah, that's it. The main thing is the shrinkage here for Ridge, and here is for both shrinkage and also the variable selection in Lasso. Okay, now let's have a look at a bigger example, which is here. Let me first of all open the data for you, so you will see it. It's where it is. Let me just open it. It takes some time because that's a huh? Wait a minute, 1 minute. Let me see. Original so here. Oh, sorry. No, it's here. Come on, take some time. Okay. So in this data set, we total have 10 million observations. So here my P attribution, I totally have 10,000, and the number of observations is 1,000. And indeed, you can see my N is smaller than P. See it? The number of data points is smaller, less than the number of total features. Okay, and I believe the first 400 features, which is X1 to X400, are binary features. So binary features means it's just 0 or 1. And binary, they're typically used for either decision, yes or no, or something true or false, or something, 0 or 1. Let's say gender, 0 means, for example, female, 1 means, for example, male. So those are binary features. And let's have a look at it. And indeed, and why is the response? Of course, you can see from X1 to X400, where the 400, 400, 400, 400, 400 is here. All of these, observations, the data are 0 or 1. Then from X401 till X10,000, here, they're just those kind of numbers. They're no longer like 0 or 1. Okay, so now I want to run the what? I want to run the linear regressions, the three techniques, which are linear LSLR, Ridge, and then Lasso, based on this relatively big data set. Let's see what's going to happen. So this is exercise 5.4. Okay, the code basically will be pretty similar to exercise 5.3. So just let me copy and paste. Although I do need to, I do need to change many things. So let me say Lasso, Rich, what's her name? Rename, copy and paste. What? Okay. And then I need to make some changes. So let's see what kind of things do we need to change. So first of all, in my main function, I need to do what? In my main function, first of all, let me see here. I can pass, let me make it to be 10K, indicating it's 10,000, features. And then I need to change these. Let's see, what are they here? Where am I? Oh, 135. The same thing? Yeah, the same thing. Okay, now we can just have a look at the functions here. So all these gonna be the same, no change. What's gonna be changed here? Let's again, I believe is it a 700 or something? I believe it's 700, but let me confirm it. Just okay, similar things. As I have total 1,000 data points, again to fix the output, in this specific example, let me use 700, the first 700 to be the training data and the last 300 to be test data without using, the model selection and then training test split. In a practical problem, you do need to, okay? I believe that for my homework, I set up to let you fix or, no, I set up, I use, consider all the data to be training data. Why? Because it's a homework problem. I want to make sure everybody's output is the same. Otherwise, I, I don't know what's going to be, is it correct or not? I just check the output will make it easier for me. But again, in a practical project, you should split randomly. Use, the function that we mentioned here, which is the model selection, and then the train test split, you need to use this in practical, okay? But in this specific example, I will use it this way. Okay, so now I'm gonna, let me see here, it's gonna say 100, and here's exactly 300, and 30, 300, 700. Okay, so now LSLR, let's see, looks everything should be the same. However, in this example, I believe I printed out for later comparison, we print the number of num beta zeros from here. Yes, I do want to print the number of num zeros. Uh, Actually, I don't have to write this. I believe I can just use MP function. Let me see here. Give me 1 second. Let me see. Just revise on the print. Non-zero, right? I can make that this way. Non-zero equals to, I remember MP dot count non-zero. Come on, it doesn't count. I remember this thing. So I will count the number of non-zeros of what? Of my betas, right? So this is LR, so it will be LR dot coefficient. Okay, now I can print the LR has these non-zero features, let's say among the total how many features? Self dot x dot shape one features. Okay, so I have this, and then I'm gonna do the same things for my ridge and lasso regression. Non-zero here is gonna be ridge R. The ridge regression has these non-zero features among the total these features correct, and then do the same thing here. Non-zero, so lasso R. Has regression has non-zero features among total features. Okay, here we go. So now let's run that to see. I believe this is correct, although I'm not sure. The running takes some time to run. You can see it's running, takes some time. Okay, here we go. Looks correct, yes. so that you don't have to. So I believe when I prepare the lectures, I just directly wrote a function to a for loop to count the non-zero. Actually, we can just directly use np here. What that means here, np dot count non-zero to directly get it. So you don't have to write a for loop by yourself. Okay, so now let's have a look at the output. It's pretty interesting. So here, first of all, let me just use a line to. So these are the, oh, wait a minute, wait a minute, wait a minute. Wait a minute. I should compare here actually. First of all, in LSLR, 100% of the features are non-zero. Okay, on Ridge, I still have 100%. But the miracle things, the magical things here, on my Lasso regression, among 10,000 features, I only have how many? I only have like 527 non-zero features. In other words, you can see it is actually a data the variable selection or a saving of my features of what almost a 95%. It's a huge saving, especially if to get a data it's costly, then you can save 95%. It's really huge. And the second thing is what we can see, let's say the selection via cross validation. Let me use another color. Let me use, let's say, the very green color. The validation select the cross validation selection for the lambdas for ridge regression this time is 20. While you can see the lambdas selection for the lasso regression is 1. So indeed, I mean they can be the same or not the same. So here my set is my lambda set is 1, 3, 5, 2, 10, 20. So this is the second thing. And I remember I should have some more things. Well, let me erase it here. I remember I have. Oh, okay. So in my code here, I printed these retained binary variables out here. Let me do it because here I do want to show the result for the binary for the binary things here. And let me see. Here is there a way I need let me see here. Okay, so yes, I can just now I'd better have a range of let me see self dot x shape. Let me see 0. No, it should be 1 because it should be a columns. And now I can do what I can do. Let's say if this beta is not 0, then I'm gonna count. I'm gonna print it because here in my slides I actually print it here. I don't want to print it to show the result of the binary issues, the binary result. So FMB MP dot absolute value of this lasso I call it lasso R dot coefficient coefficient I. If this one is greater than 0, then I'm gonna print, let's say beta I equals to, let's say, so R dot COEFI. And then let's say make it a dot 3F. Wait a minute. It should be I plus 1 because the I start from 1. However, here when we say beta, we're going to say beta 1 to beta 10,000. It's not starting from beta 0. Hence, we should add a 1. And now I think that's it because we've already printed a non-zero here. Let me run it again. It should have a lot of outputs for the Lasso non-zero betas. Let's see. It takes some time, sorry, because it's the data pretty big, it's 10 million. Oh, quick. Okay, coming. For the LSLR, that's computing for the ridge, and then time the most consuming would be for the Lasso regression. Just wait a little bit. Okay, why? That's something I really hate. Then we should run again. Holy. Uh, Actually, we don't have to run this one again because it's just taking time. I can run that, but since it's already here, and then also, I want to see the results. Okay, here we go. By the way, it's actually not that bad. As you can see, we have 10 million data here. It's not it's kind of like a moderate size of the data set here already. It's not that small, not a babies. Okay, remember here we mentioned that why did I close it? Let me reopen it. The first 400 variable, the first 400 attributes are the binary are binary, remember it to, is it 400 or whatever? Yes, here, 400. They're all 0, 1 binaries. And now let's have a look at the results. We can see 1, 2, 3, 4, 5, 6. And the seventh is 431 already. So we have 400, we originally have 400 binary variables or binary parameters. However, via Lasso, the variable selection, it selected only 1, 2, 3, 4, 5. This is 6 elements or these 6 attributes. You can see it's a huge reduction, isn't it? Which is 6/400, which is only 1.5%. And then I let me see the and then among the others, we have all this. Of course, it's just because it has 10,000, just too many to print. Okay, it printed everything. In my slides, I probably use dot to eliminate. Yeah, yes, because too long. And you can see the Lasso has 527 non-zero beta eyes among the total 10,000, which is a model selection of only 5% about. And among these, 527, six among 400 of the binary features are retained only. And that's a very good point. Why? Because typically those binary features are more like makes you more headache, trust me, in the real life, because it's binary, meaning that's 0 and 1. It's not like those kind of things that we can use, if it's a rich, for example, we can have a closed form, we can use XTX inverse to compute something. But this binary in calculation gonna make it a really, really painful. The good thing is that we selected 1.5% of these binary things. So this example, I think it's really greatly shows the power of what shows the power of lasso regression. Okay, and indeed the speed is not that bad given it's 10 million. See, yeah, 1,000 sample, 10,000 features. So totally, the total is 10 million. Those inputs. So this is, I believe, this everything about linear regressions. So we introduced the LSLR. We introduced the ridge for parameter shrinkage. We introduced for lasso for variable selection and parameter shrinkage. So in the next lecture, we will start introducing classification methods, I believe, starting from K nearest neighbor, KNN. Okay, so this is the main part of today's lecture. And we still have some time. Let me talk something about the homework. So homework one's here. It's just, homework assignments and exams, homework one. So we can, these two are the data sets. This is a description of the homework. Let me just open my local document to make it easier. First of all, do as a 1 week. So you have 1 week to do it. Uh, Write all the solution in a single Jupyter notebook file. What I mean is this. So suppose I have something, let's say new folder, let's say homework. So what I mean is you write everything, let's say you have a notebook, let's say called homework one, and the name is in this way, name it to be CPE 460 underline homework one, your name. So my name is CPE 460 homework one, and my name is Yuan Xu. So you make it like this way. And I believe here I make if your name is Harry Potter, so you make it to be Harry Potter. And this is my email address. You can just email your homework to this one document. Okay, it's only one document to be this. And each of your I have three problems. Yes, each problem should be in one as in a single cell. And before it, write a mark down on it. So what I want you to do is this. So let me make it a number. Oh, sorry, make it a row number here. Okay, so here you can change it to your markdown, and you can make it, for example, problem 1, 1, and then you're gonna have, let's say here the whatever solutions of problem 1, 1, and then here it's gonna be problem 1, 2, and then mark it down as well. And then here are going to be the solutions to problem, 1, 2, and then 1, 3. Do this. Do not just write this because otherwise I will get confused. What is the problem 1, 1? What is problem 1, 2? The solutions. You write in this way, so I know, okay, this cell is problem 1, this cell is problem 1, 2, this cell is problem 1, 3. Okay. And then one thing I do want to mention because it's the very frustrating thing I suffered. So when I prepared the class, as you can see, this is a free account. So you can see here, Anaconda gives you only 1,000 CPU seconds. If you're familiar with Anaconda and the Python coding, then it should be enough for you. However, in case let's say, suppose you have never coded Python before, you've never coded in linear regression, something in Anaconda, it may not be enough for 1,000. Of course, for 1,000 seconds only daily, because trust me, everyone will make mistakes. It's just a true normal. And then, of course, one thing, a super simple solution is, say, for example, today I solve problem 1, 1. Tomorrow I solve problem 1, 2. The day after tomorrow I solve problem 1, 3. However, I know some people will always, capture the last minute. So, someone may be working on this day or that day. First of all, I want to be very clear. This is highly not recommend. I don't want to receive very late email saying that, oh, sorry, I missed the deadline, something. Do not miss the deadline. I would highly recommend you start from today or tomorrow. So the weekend, you have enough time just in case if there are any error, mistakes or something, in your code you want to fix. One trick is that if you have the edu email, I'm not sure are all of you from U of South Alabama. If you have an edu email, try to use that edu email to sign in for the Anaconda, because here we are using, all here we are using the cloud server. So you don't have to install anything on your local computer. Makes everything easier. As long as you have internet, then it's done. It's just super simple. But just in case, okay, just in case you do not have an edu email, so you are going to be limited by only 1,000 seconds daily for the CPU usage. And also in case uh, you don't have too many days, let's say you only have 1 day to solve it, and hence 1,000 seconds is not enough. What you can do is here's a link, you can click it, and you can download the navigator. It's called Anaconda Navigator. By downloading it, you will have this. So here I've already downloaded, sorry. Here I've already downloaded here. You will have this one, Anaconda Navigator. So this is to install the Anaconda platform and including Python, including Jupyter Notebook on your local computer, so that you will never have those kind of issues like 1,000 seconds. In my personal view, this is really a very dumb setting, because 1,000 seconds for, if you're interested in data science or coding, this is really not enough. And then why should I just pay, I forgot how much dollars, like upgrade, how much, $15 per month or $50 per month for this? Why don't I just, download the Anaconda that makes my life easier, or I can just download the PyCharm, which is an IDE for Python. So if you're running a big project, you'd better use PyCharm instead of Anaconda. Anaconda is relatively small, not to mention, not to mention, run it, based on only 1,000 seconds of CPU, which is really, really low. Okay, so this is the Anaconda Navigator, which has already been installed in my local laptop. So I can, here's the Jupyter Notebook, and I click launch. and then it will open, my browser is Google Chrome. It will open a Chrome page. Here we go. Here, I can close this one. Close this one. I'm not gonna buy, but here you can see it's a local host. So this is the thing. And the similar thing is we can just, create those kind of, right click new notebook from here. This one is what I used last year because last year I was not using the cloud server. I still use the Navigator. This year I found they've already made it pretty good. So I teach based on the online, the cloud server, but I really didn't expect this. This is really, really very, in my personal view, not good, So here, let's say, I don't know, do I have anything here? I mean, you can just double click. You can, for example, you can rename it to be, for example, homework one and a CPE, what's the name? CPE 460 homework one, and then underline your name and the extension name gonna be automatically IPYNB, which is Python notebook. Okay, so now you can. This is something I wrote last year, for something so you can just, write exactly as what we did, in the Jupyter, the notebook online. And let me see how to view the line numbers. Check out. Yeah, similar. Everything the same. And after everything is done, you can just, right click uh, the folder. I actually forgot. The original folder should be under, C device and your name. You can just search it like Anaconda Navigator, .ipy a notebook where then it will tell you typically, it will be on default is this one, and then you can just go there, and then you can, find this, IPYNB notebook, and then email this one to me. Or if, for example, if it's here, you can just simply, just download it, and then go to, the corresponding place, then you just, you can just open it and then send this document to me, okay? And if you have any questions, just email me. However, I will try my best to reply your email as soon as possible. However, it may take many hours or even 20 or 24 hours. So do not, let's say on the deadline day, and it's just several hours you expect on my response. It's probably not. Another thing is, I know many professors may dislike or even prohibit you from using AI. Here, I would say you are very, very welcome to use AI because I believe nowadays, I mean, why not? If I have ChatGPT or something can help me code something, why don't I use it? Why should I everything just, everything by myself? Feel free if you want to use AI to code it. But as long as you make sure the result is correct and send me this IPYNB document, and that's it. Okay, so today we can finish up earlier. That's everything about our this lecture. Do you have any questions? You can just simply unmute yourself and ask questions. No? Okay, so if no questions, I will see you next Tuesday. Please start the homework one ASAP. Thank you and have a good night.
Thank you.
Yeah, thank you.